All right, guys, so we're going to look at work done by constant force first, and most of the time that's what we're going to have unless there's one special element that's going to be in our situation. A constant force, we would have our block on a surface with some force being applied. So if we started to apply our force information, which is the sum of all forces equals ma. All right, we're going to relate Newton's second law to energy, to work, all right, specifically. In this block situation, we only have one force that's going to cause the acceleration. So we're just going to label that as F equals ma. So when we add them up, there's only one. We don't have to worry about any other forces. Now, there is no way for this block not to accelerate with only one force acting on it. That's what Newton's law says. If we wanted to determine the rate of acceleration over some distance, we would go back to our kinematics, right? So here's a kinematics equation that we would pick. To kind of figure out how the velocity will change due to that force. And we're going to relate it to work because it has the distance in there. So if I were to manipulate this for acceleration, we would get that. So I'm going to take this and I'm going to plug it into our Newton's second law. So what we're doing is we're linking two prior chapters to our current chapter, so you can see that there's many different ways to go about solving problems. So when we get to that final, if we see a problem, you can utilize whatever tool is in our toolbox to approach it. So we're going to take that, we're going to plop it into F equals ma. So now F is equal to m times v squared minus v naught squared over 2d. Now, doing a little bit more manipulation and just changing, like rearranging how it looks, this m would be divided by the 2d, right? So we can rewrite it in a little different way. I'm going to multiply d to the other side, so we get F times d. What is F times d? That's work, all right? So we just related this to work, and what's left on the other side? We have the m, the v squareds, and then we have a 2 on the bottom. The 2 on the bottom is 1/2 mass times whatever's on top. Okay. Just one more simplification here. If we distribute the 1/2 m, this is the equation for what? 1/2 mv squared is kinetic energy, all right? So what this is saying is that if we apply a force, and specifically here, a net force, because we started with a sum of all forces. So that is a net force. Our net force is just equal to the one force being applied. So this would be the net work caused by a net force being applied over a distance will give us the change in kinetic energy. And that is whenever there is a net force acting on the object. If there is no value to the force, the sum of all forces is equal to 0, right? There is no acceleration. If there is no acceleration, the v, the velocity, cannot change. So therefore, there would be no net work done. Okay? So a situation like that would be, I am exerting a force upwards on the bear. I lift the bear up at a constant speed, and then I stop the bear at another height. Okay? If I were to do that motion over a constant speed, is there a net force acting on the bear? Say no. Why? Because constant speed means no acceleration, right? So if the net force is 0 and the speed is constant, is there a change in kinetic energy? No. Okay, so the net work would be 0 if there is no change in velocity. All right, so this is basically stating Newton's second law. Are we okay with that? Can we see that a little bit? All right. This is called the work-energy theorem. Write that down. This equation right here. Work-energy theorem. So a change in kinetic energy would have to come from an unbalanced force exerted over a distance. Okay? Work. Energy theorem. You may actually see that wording that says, using the work-energy theorem, calculate this. Okay? Energy. My G looked like a Y and I stopped. Okay, energy. If we look at this graphically for a constant force, so some force being applied over some distance, if the force is constant, our graph would look, just use a different color like that. So whatever the value of the force is, let's say, hey, it's 10 newtons. We exert that force over a 5-meter distance. Our equation for work is force times distance. Remember, that's the parallel component too, right? So what can I how can I get work from this graph? If I saw a graph like this and I wanted to get the energy, the change in the energy of the object, what would I do with that information? Good. I would take the area underneath that curve, right? Since this is the area of a rectangle, the area of the rectangle is the, for the way this is positioned, the height times the width, right? So from 0 to 10, that would be my 10 newtons, and 0 to the 5, that would be my 5 meters worth of distance. So I would get a total work of 50 joules being done. All right? So the change in kinetic energy of that object would have to equal that 50 joules. Okay? Yeah? So as an example here, let's try to use these values. If I had an object with a mass of 1 kilogram, how fast would this object move from the information provided in the graph if it started at rest? We'll specify that it's not moving at the time we start exerting that force. All right, just to reword the question, if we didn't write it down, it would be asked something some way like this. An object that is 1 kilogram has a force exerted on it according to the information given in the graph. What would be the final velocity of that object if it started from rest? So all of the information is given as the mass of the object, that it started from rest, and then data that is on that graph. Okay? So the way to go about doing that is remember that the work done is going to be equal to the change in kinetic energy. To find the work done, you would take the area underneath the graph, which is what we just did. Okay? So the work done is equal to the area, which we calculated from 10 times 5 gave us that 50 joules. But the work done is also equal to the change in kinetic energy. So that means that the kinetic energy is going to change 50 joules. And that has to equal 1/2 mv squared for the final velocity minus the initial, which is 0. So you don't really need that. And now we just solve for what we want. So we would multiply the 2 over, so you have 2 times the 50 joules divided by the mass of 1 kilogram is equal to v squared, so we have to square root everything. So is that equal to 5? No. Okay, so couldn't do the mental math.
Would it also work just plugging numbers into the kinetic energy equation?
So we got that the answer is 10 meters per second. Okay. So if we divided by the 2, right, it would have been 25? Okay, because yeah. Okay. Does that make sense for just a different approach to a problem? All right. So on the next topic, we're going to look at a variable force. Instead of it being a constant force, let's look at a variable force. Can I edit that? No. And the only variable force we're really going to work with is a spring force. And the spring force equation is force of a spring is equal to negative kx. The negative is conceptual. You will not apply it mathematically. It only means that it's acting opposite the applied force. If I apply a force to stretch a spring out to the right, the spring will exert its force to the left. All right, K is the spring constant. It is basically telling you how stiff the spring is. The higher the number of the K, the stiffer the spring will be. So if I had a K constant that was equal to 100 and the units are newtons per meter, that means it would take 100 newtons worth of force to stretch it 1 meter. So by using the spring force equation, if I said I had a force and I wanted to stretch it 1 meter, this is a notation, okay? Did you ever see in math where they say f of x, f as a function of x? So I'm just kind of using that notation and putting a value in, basically stating it's my given, all right? So don't get overly excited about that. Okay, so if I plug it in 1 meter, I would have a K value of 100 newtons per meters, and then multiply that by 1 meter just from the Kx, you would see we get 100 newtons. If I stretched out the spring 2 meters, guess what I would get? 200 newtons. The force for 3 meters, guess what I would get? 300 newtons. So what happens to the force? It's variable. That's supposed to say variable. Whereas when we are applying a force to a block, and having it accelerate, it would be the same value of the force. If we applied 10 newtons, it was always 10 newtons. We wouldn't increase or decrease the value of that force. Okay, so, and again, that would be to either stretch or compress the spring, if it's a compressible spring. So what would the data look like on a graph here? So if I exerted a force of 100 newtons, that would stretch or compress 1 meter, right? 200, 2, 300, 3. So if we plotted that out, 1, 2, 3, we would get a linear graph. That should be linear. Okay. Pick any 2 points. The slope is going to be equal to the change in force over the change in stretch. Okay, the distance would be the stretch. If we look at this equation up here, if we take our force divided by the stretch, we would get the K constant. So that slope is equal to the spring constant K. If we had another set of data, like 2 springs, and the slope was less steep, that would be a softer spring, right? You would need less force to stretch it out to that 1 meter, okay? Now, how would we figure out the work done by this variable force from this graph? So just like we solved it the last time, for the last set of data with the constant force, the area underneath the curve on this graph is going to show us what the work done is. Okay, it's still force and distance. It's still a force and as a function of distance graph. The area underneath a force as a function of distance graph can always give you the amount of work done. Yes?
Can we just say to multiply the x and y coordinates together?
You can't, because it is a variable force. So unlike the constant force where at every distance the force was the same value, this one it's not. So you can't just multiply force times any distance. You have to actually take, it works as the average force, really. If you were able to take the average force for a linear relationship, it will work out. Just to show you that, what would be, so if I drew a line at 150, if this was drawn well enough, let me see. If I were to draw a line at 150, right, the area here would equal the area here, right? So 150 times 3 is 450, right? 450 joules. So taking the average force works. If you want to think about it that way, that's good. Because if we just take the area of a triangle is what? Right, so the area is 1/2 the base is the distance, times the height, which is the force. You get 1/2 of the force, the total force is 300 newtons, times the base, which is 3 meters, which gives you that 150 times 3, which is 450 joules. So you can see that the change in spring energy is going to be equal to 450, whether you think about the average spring force from 0 to its max, or the area underneath the curve.
Will there always be one? Like, there will always be, is that max, like actually the max? Or?
That would be for the situation.
Oh,
Okay, so if I wanted to figure out the work done to stretch it out only to 2 instead of 3, instead of 15, you can pick any 2 points. If I wanted to figure out the work done, how much energy I would have to input to just stretch it from a point that was already a stretch of 1 meter to a point that is 2 meters, I would just have to solve for that area. Does that make sense?
Yeah.
Where you'd have to use the area of a trapezoid there. Or 2 triangles and subtract them, however you want to think about doing it. But it's the area underneath the force as a function of distance curve that will give you the work done. The next thing we're going to do is just look at the spring force, the spring energy equation and where that actually comes from. Well, we'll need that. So just from the area of that graph of force, and I'm going to use x as spring stretch here, right? So at any value of x, at any value of force, the area underneath that graph, which will be the work done, would always be 1/2 the base times the height, here the height being the force, the base being x. But the spring force is k times x at any point. So we get 1/2 kx, which is the force, substituting in from this equation, times x, where we get the work equation for a spring is 1/2 kx squared, which we've already been given. Okay? So the work done would be equal to the potential energy stored in the spring. So when I talked about work yesterday, and I said, every time you hear work, think about the change in energy. What form of energy is changing? Okay? If we picked any 2 points, that's where we would have the difference between any 2 stretches. If we wanted to figure out somewhere in between, that's what that equation would be. Okay? So we can see that this work solve from the graph will give us what the potential energy equation is. This might also be a helpful equation for you, right? So if you can see that from here, that the force is kx, you might sometimes know the force. So instead of working backwards and figuring out k and the x value, if you know the force, you can simply go to that one, and it's basically proved from the graphed data. So what would be the total amount of work done on an object that has been through an experience that mimics this data? Something that can actually mimic this motion would be a car is stalled. You try to push it to get it started. You start exerting a force and you increase that force until it starts to move. You then maintain that constant force while you're pushing the car, but the car accelerates away from you and the force that you're exerting decreases until you remove your hands from the car. So that's when you stop exerting the force right there. So that would be the type of situation. So we can actually figure out how fast would the car be moving after it has gone through that, change in force. Okay. So all you need is the intervals. So this is one shape, breaking it up into the areas. How much work is done over the first 2 meters? 2 joules. Joules. What's the work done in the second 4 meters? How many joules? 8. 8 joules. And what's on the last one? Another 2. Okay, so the total work done would be equal to 12 joules. And again, we can extend this problem and solve for other things. So if we knew the mass of this car, we can solve for how fast it's moving at the end. I don't think we need to go that one step further in this video. Okay?